So it's great to have Lorenzo Zambotti here, who's going to give the second of our lecture courses here, this time on regularity structures. And so you're going to tell us a bit about algebra and renormalization, and then the second part of this lecture today is going to be given by Felix Otto in Michigan. So please.
Thanks, Hendrik. So I would like to thank the organizers of the workshop for inviting me. It is a big responsibility to try to present you this topic. So renormalization in regularity structures. In fact, so there are two mini courses on regularity structure. So one by Felix Otto on the reconstruction and integration point of view, and one by myself on renormalization. So we have discussed together and we have decided to base ourselves on the same review paper by Martin. It's easy to find on archive. So this gives us some kind of lecture notes. This is actually, we didn't ask Martin for permission, because I guess you don't mind. Okay, and so it's again a review paper, so it's relatively short, not self-contained in the sense that there are no proofs, etc. But it explains in one, so in 20 pages, it explains all main ideas, in particular on the dynamical 543 model, and this looked a particularly good choice, because it seems that this 543 model is a kind of unifying theme for the four courses. Okay, so this looks like a good start for good discussions and interaction for the four courses. Okay, so okay, now I want to explain a little bit the origin of this 543 model. So I have a disclaimer. Really, my knowledge of physics is very poor. I apologize if I omit names. So really, I did my best, but it may not be optimal. So anyway, the aim of constructive quantum field theory was to find physically relevant relativistic quantum field models that were also mathematically consistent. So I will explain in this 543 example what that means. So in particular for the Euclidean case, which is related to probability theory, starting from the 60s, there has been a very important activity around these names. So Szymanczyk, Nelson, Gliman, Jaffe, Osterwalder and Schroeder, Guerra, Rosen and Simon. So for instance, one major open problem is the Yang-Mills theory in 4 dimensions. Okay, so not 3 dimension, not 2 dimension, but so the big problem remains open. Okay, so in particular, so our center of interest is this 543 model. So this was built so in the 70s, in the 80s. So again, a list of people with different methods and constructions of this object. So Gliman, Jaffe, Feldman, Osterwalder, Magnen-Senior, Rivasso, the Italian community around Galavotti. This Balaban has been already mentioned several times, Bettel and Federbush, and so the paper by Bridges, Fröhlich and Sokal that I will mention later again. Okay, so what is the model of interest? So let's consider the torus in dimension 3, And so you would like to construct this probability measure, a normalization factor times this exponential of Hamiltonian, where you have the gradient phi square, quadratic term, and a quartic potential. Everything integrated over the torus, and then times, say, this formal Lebesgue measure on functions, where so m is a real number and lambda is positive. Okay. So the problem, so the mathematical problem is that this measure is ill-defined. Why? Because, well, if it were easily well posed, then essentially it should coincide with this Gaussian measure multiplied by this exponential of this integral of the fourth power of phi, where delta is the Laplace operator on the torus. Okay. However, it is well known that this Gaussian measure is supported by space of distribution on T3 in the sense of generalized functions. So the space of functions has probability 0 with respect to this Gaussian measure, and therefore almost surely this term is ill-defined. The quartic nonlinearity is ill-defined. Okay, so this lack of local regularity is known as the ultraviolet divergence, opposed to that of infrared divergence for large scales. So this has been already mentioned by Antti this morning. And okay, so the higher the space dimension, the worse this lack of regularity of phi. Okay. Okay. So again, this work in the 70s and beginning of the 80s was centered about constructions of this otherwise ill-defined object. Now, the SPD story, which is related to this model, begins in '81, when Parisi and Wu proposed to construct this measure as the invariant measure of a Markov process, which may be constructed in different ways. One possibility is via this SPD. So this is a simpler version of what Martin has explained for Young-Mills. Essentially, you consider the gradient of the previous Hamiltonian. This becomes the nonlinearity of your equation. Then you add the space-time white noise, which is a centered Gaussian random field on R plus times T, so the torus, which is, say, has independent values for different space-time points. Okay, so this in '81, this was a physics paper. They proposed this problem, but then mathematically this is again very, very difficult for more, say, analogous reasons. Again, this is defined, etc. We'll mention this. So anyway, at least on the two-dimensional torus, there was some successful attempts to solve this problem. So the first so rigorous construction was done by Ionalazino and Mitter in '85. Then by Dirichlet-Forbes, Albeverio and Röckner in '91, and then so strong solutions were obtained by Da Prato and De Buch in 2003. So on the other hand, the three-dimensional case had to wait until the paper by Martin in 2014. And the introduction of regularity structures. So this will be the topic of this two mini courses, so mine and Felix. So we'll try to explain you at the same time the general theory and the concrete computations on this example of the 543. Okay, so today is more, so my lecture is more of introduction, so I want to mention that there has been a very large and very interesting activity. So there is another possible approach which has been successful, and it is based on paracontrol distributions. So it is the theory given by Gubinelli, Imkeller, and Perkowski, and so the paper on the 543 is this one by Catelier and Chuk. So another approach which is based on Wilson's renormalization group is due to Antti, so maybe he will have time to mention this in his mini course. Now, okay, I will mention this perhaps later, but also Martin said that when you use regularity structures, at the beginning you have only local in time solutions. Okay, sometimes you also at the end you only have local in time solutions. Now, if you want to discuss the invariant measure, this is not satisfactory, because the invariant measure should be the long time limit of your law, and if you have only local in time solutions, you cannot take the limit t goes to infinity. So there has been some again very significant progress on in particular, at least for 543. Murat and Weber proved that you have very strong estimates on this dynamical equation, which imply in particular ergodicity. And okay, to make the link between the recent theory and the more ancient results, so Heirer and Matetsky proved that indeed, so the dynamical 543 has as an invariant measure the 543 model which had been constructed previously, and so this goes through the results of Bridges, Fröhlich, and Sokal, and a lattice approximation. Okay, so this is to mention that it is possible, and it is one of the aims, among other things, of this semester, probably to relate these two words, okay, to each other, although this is not immediate. Okay, so it is not trivial. It takes some work to even in this situation to show that the new theory gives the same objects that that had already been constructed before. Okay, by the way, so since there is a scaling limit in the title of the semester, so so this is there is a lattice discretization, so there is kind of a scaling limit. So another beautiful scaling limit result is this one for the two-dimensional case. So Murat and Weber proved convergence of the two-dimensional Ising-Katz model to, 542 after scaling limit. Okay. Yeah, perhaps you notice that this is Beamer in format 16:9. I discovered recently that you can do that, but so when I changed the format, I didn't notice that something was.
When you speak of scaling limit, what do you mean?
Well, it means that you. So what's?
I'm saying this.
You mean a continuum limit, probably, is better word. The reason why there's some confusion is scaling limit. Many people in physics think that scaling limits are scale invariant. These ones are not, because they have a mass.
Okay.
And so what you're doing is approaching.
Yeah.
So
Yeah.
they're
Sorry.
not,
Okay.
they're continuum limits.
Yeah. Okay. Sorry. Continuum limits. Do you confirm? No. Yes. Okay.
In the scaling limit, there is no parameter, scale parameter, by definition. Nothing carries the parameter like mass scale or something. Nothing.
So what I mean?
The coupling constant in pi 4 has a dimension. And in the scaling limit, it goes away. The bare coupling constant in the continuum theory goes to infinity.
Okay.
This is a different problem.
Yeah. Okay. Sorry. No. Okay. Here I mean that there is some some discrete process which converges to a continuum process.
Yeah, I think the simple way to say it is if you were able to do this continuum limit so that the mass was 0 at the end, that would be a scaling limit.
Okay.
That's a bit harder.
Okay. Sorry about that.
Going goes to critical.
Okay. So yeah. So this in a sense completes the program of Parisi and Wu. Okay, although again there is quite a lot of work. Okay. Now, of course, this ultraviolet divergence, which is present in the invariant measure, is also present in the dynamical equation. So here I write simplified version, so what is the point? So okay, let's introduce just for clarity. So some function space C alpha, which okay has a precise definition that I'm not going to give. This is a misprint. Parabolic base of space B alpha infinity loc. So this coincides with the usual parabolic C alpha space for positive non-integer alpha, and for negative alpha, it's some space of distribution on space-time on which you have a topology and etc. And alpha gives a measure of the regularity or lack of regularity of your distribution. So the point is that if I consider the solution to the linear equation, so I forget the nonlinearity, then this belongs to C alpha only for alpha less than -1/2, and therefore I am in 3 dimensions here. And so again, the cubic nonlinearity is ill-defined. So that's why it took almost 25 years to do what Parisi and Wu proposed. So in fact, the 543 model is only one example among many. So there is a whole class of equations which are now called the singular stochastic PDEs. So another prominent example is the KPZ equation. So here you are in one space dimension. This is the parabolic PDE. And Xi now is space-time white noise, but not in 3 space dimensions, in 1 space dimension. And so the phenomenon is the same. It's not u, which is now a generalized function. It's the derivative of u is not a function. It is a generalized function, and this square is ill-defined. Okay, so even for polynomial nonlinearities, we do not know how to properly define products of random distributions. And okay, in this mini course and in the one by Felix, we are going to discuss Martin's approach to the renormalization of such singular equations, so that you could more or less write in this slightly more general form. So it does not mean that you can consider any function of u, delta u, and psi. Far from that. But okay, there is a larger class which is not necessarily polynomial, for instance, in u, etc. Okay, but anyway, we will try to concentrate on the 543 example. So again, when you hear the expression singular stochastic PDEs, nowadays this means that you have nonlinearities where you're supposed to put generalized functions, distributions. Okay. Okay. Now, this is one of the theorems that you find in this review paper by Martin. So consider, now again you are on the torus, you consider a modified version of your noise. So now C epsilon is smooth in space-time. Okay, so I didn't write, but rho epsilon is a modifier in space-time. And so you consider your regularized equation, and you also modify it by adding this term C epsilon times phi epsilon. Okay, and then the theorem is there exist constants C epsilon which diverge as epsilon goes to 0, and the process phi such that phi epsilon goes to phi in probability, and phi does not depend on the modifier rho. Okay. Okay. In fact, so this is just a very simplified and synthetic version of the general result that you can obtain. So you have many more information. So for instance, you can in fact write the constants explicitly, and they behave exactly as at some point Antti wrote on this blackboard. So you have one term which is proportional to 1 over epsilon, and another term which is proportional to log epsilon. Okay. So okay, I was thinking, this is to me one of the, say, mysteries of all this. So it is of course very reassuring that you get say diverging constants which look the same, but in some sense it is not so clear, at least to me, why this is the case, in the sense that what you're doing here is completely different from what Antti was explaining. Actually, so this equation is also quite strange from a stochastic analysis point of view, because you are now modifying in space-time, but so in particular also in time. So now psi epsilon is some Gaussian smooth function, but there is no anymore independence of increments. So what you obtain is not a Markov process, so there is not an invariant measure behind. So in some sense we have drifted away from the static 543 model. Okay, this is something different. This is intuitive from a PDE point of view. Okay, PDE people do not usually add this kind of Gaussian smooth function, but their theories cover this equation. Okay, so you can say classically what phi epsilon is. It's again a smooth function, and so this is easy now to explain to someone else and say, okay, I consider a smooth function which is an approximation of some very rough object. Okay, but at the same time, this smooth function does not have necessarily the same properties as So maybe I have lost some good properties that my rough object will recover in the limit. For instance, the Markov property. Okay. Also, the result, in fact, that you can get is much stronger than this. So it's not only that phi does not depend on the modifier. So in fact, phi can be a posteriori described independently of the approximations. Okay, so and then it would be Markov process, etc., etc. So in this, so again, also for Young-Mills, Martin mentioned that you can regularize, but so this has its own then say problems. Yeah, so this is one of one of the things that are perhaps an interesting problem for the coming months of this semester. So to really understand why you, for instance, you have the same constants here as in what was explained this morning, which is of course related to the fact that in the end the invariant measure is the correct object. But as I was saying before, it is far from easy to prove, okay, to obtain. Okay, anyway, it's good news that you do have constants with a good behavior, which was already found in other contexts by other people. And okay, there are at least two questions that deserve to be discussed here. So what is this term that I have added? So is it legitimate to modify the equation just because you want to obtain a convergent solution? Okay. So this is the renormalization step. So it amounts to a modification of the solution. Yes, I mean, of the equation, and therefore of the solution to the equation. Okay, so is this reasonable? So am I allowed to do that? Have I just changed the problem because I could not solve the previous one? Okay, is this still the good object? And in other words, so which one is the correct equation? So with the term, with the counter term, or without the counter term? So
may I make a point?
Yes, please.
When people do constructive field theory, they get in the static case, they get this measure,
Yes.
543.
Yes.
Well, you put in several cutoffs, torus, but you put in an ultraviolet cutoff.
Yes.
Putting in the ultraviolet cutoff, you need counter terms. Okay, so cut it off and put in the counter terms.
Yes.
Okay. And then you look at the Langevin equation for that.
Yes.
Is it not without modifying the noise?
Well, you are doing more than just modifying the.
No, I'm just putting in the counter terms of the static theory. One of the mysteries is why are these same? But if the counter terms of the static theory are sufficient to regularize, I mean, if you don't regularize the noise, you have a process in the space of distributions, right? If there was no interaction at all, no problem. You can discuss the process in the space of distribution. But now you have interactions. For the interactions, you put in the counter terms at the level of your putative invariant measure, okay? And then would it not regularize the Langevin, the solution without regularizing the noise? That's what I'm saying.
No. So you still have the quartic term, which is defined. So you are not.
No, it's a smooth field there.
What is smooth?
So basically what Prof is saying is take a lattice cutoff and look at the...
Lattice cutoff.
Okay, so you discretize the space.
Yes.
Well, okay, but that's almost
You need a strong enough
it's
cutoff.
more difficult than this to prove convergence. So for instance, Heirer and Matiecki, what I mentioned here, do
Yes.
that. So, but they do it after they built the whole theory and prove that there is a limit. You see?
We should discuss it afterwards, because
Maybe, but no. I mean, it's. So I'm saying that what you propose is not easier.
I'm
The
not
proof
saying
is
it's
not
easy.
easier than what I'm saying. Okay.
The fact that the counter terms are the same, that's an explanation possible.
Maybe yes, but okay. We can try to come back to this later. Okay. Yes. Okay, so I want to show an analogous phenomenon which is much simpler, but I find this instructive. So consider now ODE in a finite dimension with some smooth coefficients B and F of this form where B epsilon is a smooth approximation of a Brownian-Bosch, like for instance, again, a modification of B. Then what happens as epsilon goes to 0? So the Wang-Sakai result states that X epsilon converges, so the solution to this ODE converges to the solution of a SDE in the Stratonovich sense. Okay, so if you want to obtain the Ito SDE, then in fact you have to define a different process, which is solution to this modified equation. So you see from here to here I have added this drift, and then indeed in this case X epsilon hat converges to X hat, which is solution to the Ito SD that you perhaps expected from the beginning. Now, in fact, 2 is a renormalization of 1, just like, so in the previous slide, this linear term made my equation a renormalized version. So this is a kind of a counter term, so there is no divergence here, but still I have added something which was not there at the beginning in order to obtain something in the limit. Okay, so this is quite simple in this situation. So the explanation is that if you want the Ito product, so the Ito integral here, you want that so your dB okay, has to be independent of f x hat. So dB has to be so the interval has to be after the time when you compute x hat, and this is not reasonable for this kind of approximation, because again you are modifying in time, so you are losing the independence of increments, and so this is, in fact, it is reasonable that this converges to the Stratonovich integral. And if you want to restore the Ito integral, you have to prepare your product by subtracting the related counter term. Okay, so in some sense, renormalizing means choosing the correct approximation for the product in this case, but it's the same. So 543 is also a product. It's a cubic. So it means again choosing the correct equation which approximates the product, the object you expect, you want. Okay, so this is a kind of We'll see this better later. Okay, so still this is okay. Perhaps here I am just repeating the same principle in the general case. So for any kind of this singular SPD, you can consider the regularized equation, and then okay, this is well defined with classical techniques. But what happens as epsilon goes to 0? Now we need a topology on Xi, okay, in such a way that the map from Xi to U is continuous, at least for the regularized version, and then Xi epsilon converges to our, for instance, space-time white noise. But so these two requirements are contradictory with each other. So for the first, you need essentially positive regularity, and for the second, you need a negative regularity. So you don't have like a classical Sobolev space where both properties are easily true. Okay, and okay, indeed, for a large part, regularity structures are about finding the correct topology where this holds. And okay, we'll see that this is quite non-trivial. So in fact, the theory is based on so this kind of program. So you construct a space which is called a space of models. Okay, as usual, so I prefer to show you the picture. So this is regularity structures in an image. Now here you have your noise, which lives in the space of distributions, not necessarily tempered. So here you have so here you have your space-time white noise, and this is the regularized version. Now you use the equation, the regularized equation, to get a solution U epsilon, which is a function, but okay, you consider this again as a distribution. And then you don't know what to do with the U epsilon, because you have no theory that guarantees convergence. Okay, so you are lost. What does this theory propose? So you construct a space M, which is called the space of models, together with a lift of your noise to some point here, x epsilon. Okay. Okay, and then there is a big function phi, which is called I realized that this is the same as the 543 model. Sorry, that's a bad notation. Then I have to change the letter. So there is some map from M to the distributions, which makes this diagram commute. That means that phi of Xi epsilon is U epsilon when epsilon is positive. Okay, but now the kind of mysterious effect is that this map is continuous. So there is some topology on this mysterious space M in such a way that this solution map is continuous from models to distributions, which means that so you have taken a function from Xi epsilon to U epsilon, which is not continuous, and you have factorized it into in the composition, okay, of two functions. So one which is continuous, it is this one, and one which is okay must be non-continuous, otherwise everything would be continuous. Okay, one lift which is discontinuous, and then one step which is continuous. So this is kind of strange, but in fact it's the idea is that if you can guarantee that x epsilon or some modified version will converge, then phi of this convergent object will converge. Okay, so in a sense you have separated the problems. You can concentrate on what happens on this space of models, and then the solution map will do the rest. Okay, and the advantage is that what you have on this space of model we'll see is going to be a finite number of explicit functions of psi. So you're not working with a mysterious function u which you don't know exactly. So you will put your hands only on psi, which is your noise. You choose it. So okay. So it's not very intuitive at first, but it works. So let me repeat this. So you have this strange space of models M with a metric D. It's very important. So it has to be a metric space, otherwise continuity is not well defined. So you have a first choice, a canonical lift of every smooth psi epsilon to a model x epsilon in this space. Then you have a continuous function which is defined on the whole space of models with values in distributions, such that whenever you start from your canonical lift, then u epsilon is the solution to the regularized equation. So again, it's the commutation of this diagram. Okay, and then, so this is the renormalization part. You have some group action on the space of models, which allows you to modify your canonical lift and obtain another object x hat epsilon, which again lifts psi epsilon, but then converges as epsilon goes to 0. So it's what, okay, you see on this fiber, you have both x epsilon and x hat epsilon. But then, so x epsilon was maybe not converging anywhere, while x hat epsilon may converge. Okay, so if you are good enough, you will find a different lift which does converge. And then here you define u hat epsilon, which is phi of x hat epsilon, and u hat, which is phi of x hat. So again, by continuity of phi, this will converge to this without additional effort. Okay, this is what I wrote here. So you obtain a renormalized solution u hat as phi of x hat, which is, by the way, also the unique solution of a fixed point problem. So as I was saying, one second, as I was saying before, you can describe your limit object independently of the approximations. Okay, that's why so that's why this theory is strong, because then you can have different approximations, and it will be relatively easy to prove that they converge to the same object, because the same object is defined also in itself. Okay. Yes, Milton.
What happens if you take the quotient of the model n with respect to the group action?
Why do you want to do that? So, for instance, in the KPZ equation, let's go back to basics. So, okay, I didn't put the slide, but the renormalization means that you subtract a diverging constant, okay, and then you can add a finite constant. So, and this will be the action of the renormalization group. Okay, so why would you take the quotient of this with respect to this action?
Because, okay, So in the KPC case, that would be like saying that Galilean transformations don't matter.
Uh-huh.
Yeah, but that's very special.
Yeah, that's
So-
very special, I know, but that's why.
But like in 5.4, you cannot implement the action of the renormalization, but just the transformation of solution space.
Okay.
In general, it counts.
Okay. Well, let's say that certainly, again, this group action allows you to act on the model and therefore also on the solution. So this will be part of the of the theory that the solution is not unique, because again you have this group which can act on it, and then you may choose the solution that has special properties of particular interest. But again, this is you see also in this setting sorry, you have two notions of solutions. Actually, you can have a one-dimensional set of such notions. They are all legitimate. So, and it's the same for these renormalized equations and solutions. Yeah. Okay. So again, I want to mention that this map, which we can call the solution map, is inspired by what Terry Lyons did first in the case of rough paths. So if you know something about rough paths, so you will recognize that so here you may have your say path, and then this would be the lift, so the enhanced path where you can have like additional information, and so this may be the solution map which gives you the solution to a stochastic equation. And again, so the main insight by Lyons is that this would be continuous, while this would remain discontinuous. But again, this allows to separate the analysis from the probability in a sense. So you solve SDE by doing these two steps separately.
Where are the counter terms in this new picture that you have presented?
So the counter terms are here. So
Counter terms are phi dependent, and this picture looks like it's only
Are
phi dependent.
sorry, phi dependent. What do you mean?
Phi meaning the random field phi. The counter
No. Here, no. Okay, no. Here we no. Okay. So we work on situations where you have constants. So the counter terms are constants.
Here I only.
And but in fact, so the group action is general. So okay, maybe we'll come back to this here. But so I wrote here that I have really constant. So these are really constant.
But what I mean is that C epsilon phi epsilon, the term that you had, it's phi dependent.
Okay, because you multiply C epsilon by phi epsilon. Okay.
And so this field X, this
Okay.
model X or X hat,
Yeah.
it depend only on psi or also
No.
on phi.
Alors, okay, good question. So I said that here you have objects which are only functions of psi. They do not contain so phi or u. Okay, they do not contain. Let's say u. It's on this slide. U is a result of this operation.
Then I'm confused because it looks like X hat is going to be equal to psi plus that term C epsilon.
No. You will see. So this is the magic of the theory. No. We'll do the computations. So, but not now. So just if you are still here for 2 or 3 days, then no. Really, that's really important. So I think I have an example here. So in M, you will put a finite number of relevant explicit products which contain only essentially psi and the heat kernel or variation thereof. Okay, so this is one example. psi epsilon times G convolution psi epsilon. This could be also written in Feynman. So in particular, this expectation could be also written in Feynman diagram representation. But so why does your canonical lift fail to converge? So because, for instance, if you compute the expectation of this object, it's very simple. It's this quantity which converges to G of 0, which is infinite. Okay, so you are choosing classical objects when epsilon is positive, but when epsilon goes to 0, they fail to converge. They can fail to converge. And that's why you need to modify your model. Although, again, as I was hinting before, you're modifying it because this was a bad choice in the beginning. So. Okay, but you get this kind of terms in the model, and then the solution again is the result of the solution map, as the name. So this is really part of the magic of the theory. And okay, I want to mention at least this, which is very important in Felix' course. So the theory of regularity structures is based on a deep generalization of the classical Taylor expansion technique. So after Antti explained this morning, so the perturbative approach, there were also expansions, Taylor expansion, but this has nothing to do with that. So the theory is non-perturbative. Okay, the point is that you will use the products which are contained in this model, so in order to approximate your solution locally with a generalized Taylor expansion, okay, which is a random Taylor expansion. And yeah, a nice quote from this paper. While solutions to equations like APZ or 543 may appear to be very rough, they can actually consider to be smooth, provided that one looks at them in the right way. Okay, so you have to understand them. You have to talk to them. Okay, and in fact, this has been inspired by rough paths, in particular by the controlled path approach by Massimiliano. And okay, the space of models will be the space of these generalized monomials. So this will be explained by Felix better. Okay, so again. So so this is a nonlinear space. For instance, if you consider, okay, let's try to do this. Classical monomials are functions, okay, say on R, okay, something like that. Okay, suppose you stop at some point. Okay, of course, this is a nonlinear space. Okay, so in particular, xx squared, you get a parabola. So monomials are inherently nonlinear. Okay, and if you take okay the sum of two functions like this, it's not of the same form anymore. Okay. So it is not a linear space. If you multiply this by lambda, it's not the same form anymore. So you need a nonlinear set like this form, okay, and you need a nonlinear topology on it. So once again, for rough paths, this had already been understood very well by Terry Lyons, who proved that the solution map could not be realized as a continuous map from any Banach space to And so this makes the part of the difficulty of the theory, that you have to introduce so special objects that will be explained in order to have a theory of these generalized monomials. But anyway, so I insist. So the idea is to reduce the problem to the construction of some objects, which is so a finite number of explicit functions of your noise. And then, thanks to this mysterious solution map, the solution will come out automatically. And actually, you will have very strong information on this. Okay, so I'm happy to stop, and thank you very much.
Thanks for the first lecture. Are there already questions? We had some questions.
So when you say this phi is mapping to the solution,
Yes.
solution of which PDE? The standard one and the modified PDE. How?
Okay, good question. So,
What was the question?
okay, the question is, what does this map in fact? So, what I'm saying is that this sense, the requirement is that this sends this to this, where this is the equation. Okay, so then if you, now this is a very non-trivial fact, in fact. So if you now modify your object, so a priori you have no information. This could be anything. Okay, so it turns out that u epsilon hat would be again the solution to a PDE. Not the same. It would be the renormalized equation with some counter terms, but the structure is very similar. So essentially it will be a f epsilon.
That's given by the phi.
Yes, but the phi does not depend on epsilon. So it's the same solution map, which gives at the same time the starting equation and the renormalized equation.
But the u hat, which is also in the image of phi,
Yes.
what that doesn't satisfy any.
Yeah, okay, that's more complicated because, like, for instance, here this will have become infinite. Okay, yeah. Well, okay, you still have a PDE, but on another. Okay, this will be part of the course. But you're right that you lose something.
This is very unusual. And does this trick only work if you have to renormalize something which is linear in the field phi?
No.
Super renormalized.
Yeah. Okay. Sorry. Yes, this was my last. This applies to what is called by Martin subcritical equation, which corresponds to renormalizable theory. But still, there is a large class, much more general. That.
Well, I mean, the counter terms. Do the counter terms have to be linear?
No.
Not necessarily.
They are general function. I can show examples tomorrow.
But it's a bit mysterious, like Margarita asked. You have two choices: either to
I know.
modify the noise or to modify the equation.
It's crazy.
Okay.
Yes, please. Please.
I have one small addendum to what I said earlier.
Please.
That Roland says you can put it on the lattice, but you don't have to put it on the lattice, because if you look at the linear process after you've cut off the static measure, okay? The linear process has a covariance. That's the Austrian-Nuremberg process.
Yes.
That covariance is cut off. It's a cut-off covariance, and therefore the process is realized almost surely on nice functions, not on distributions.
Yeah, but then you are changing the leading differential operator. It's not the Laplace operator anymore. So
No, of course I'm changing the Laplace.
okay. Then again, how do you control the convergence? It's
The standard procedure for continuum regularization is to change the Laplacian, okay? Make the covariance highly cut off, so that the measure is realized in almost smooth functions. That's the idea. It's the same circle of ideas. then you don't regularize the noise at all. You
Okay.
get the Markov property all the time.
Yes.
So perhaps it's time for coffee, no?
Yes.